when you install IMAT for the first time you start it, you get this welcome screen where you can choose between whether you want the light or dark theme. My preference is a light theme. The dark theme doesn't make nice screenshots for reports, and I also found that it doesn't create nice movies, but each onto its own. Feel free to choose anyone you use there. I've already got a license set for the purpose of this training, just to speed things ahead. But when you install IMAT for the first time on your machine or a client's machine, there will actually be an intermediate step that takes you to the license panel where you can enter your license details. So the idea is that it is easy to get set up with IMAT, especially for our clients. So keep in mind that IMAT is designed around Mine users, not so much consultants, even though there's quite powerful features that will make consultants' life easier. It's really designed for the miner to rapidly and easily build models and do analysis with various kinds of data. So each time after you, when you start IMAT, you'll be welcomed with a screen where you can either create a new project, open an existing one if you have already opened one. This is a new installation, so I don't have a recent one, or you can close and continue manually. I'd also like to mention that IMAT doesn't have a formal help manual like our other software like Flat3D or any of that. We try to be modern, so what we do is create a series of how-to videos. So IMAT's got a YouTube channel. And the idea is that each time someone asks a question or there's a feature that needs explaining, we add it, we do a quick screen recording, we add the YouTube video to our YouTube channel and link it from within IMAT. So here's the first example. You can click on this and this will show you how to set up an IMAT project. And everywhere throughout the application, there are links to YouTube videos on how to do things. Now, this list is hopefully going to grow in future. There's only a handful of videos as of current, but hopefully in the next year or so, there will be a video for most of the items in IMAT that's not intuitive. You can just click on the YouTube video and it will show you how to do that task. For this example, I've got a real Mine data that I've heavily modified so that it cannot be recognized. I've got real seismic data with source mechanisms that I'm going to use. I've got several mining steps in the mining sequence for this mine. So we're going to import the seismic data, import, for example, the mine's block model data. We can look at some borehole data that we can import, and then we're going to use all of that information to build a model. When you update IMAT, you don't have to reinstall the software. The update mechanism is actually quite simple. When you start the software, and an update's available, Dialog will be in the bottom right-hand corner notifying you that an update's available. Yeah, so each time you do an update, also it tells you what the new features were that were added when after the update. So here you can see in the bottom right-hand corner tell you that there's 20 updates to IMAT or 20 modules. You can click on that and either update from there or go to help check for updates. These are the list of modules that in IMAT that's can be updated. And just follow the prompts, update the software. So it's currently downloading it from our servers in the US. And then just the software will automatically restart and the update will be available. There's another useful feature that I would like to mention is that tools submit a bug or feature request. So whenever you want to, you found a bug or you've got a question or you've got a feature request, you just fill out this form. If you've put your name and email once, then it will remember all of that. But you can specify then whether it's a bug. So I'll just quickly fill in this. I'll just leave that empty for now. So I want to file a bug or a feature request. It's extremely important. Just put that out of the way. Extremely important. Give it a name. Say IMAT is broken. And then at least provide some context. IMAT broke after updating. If you do this, that files a request in our ticketing system. It files a request in, so you get a ticket, GitHub ticket that's assigned to you. It sends us developers an email of your application's log file, and we know how to respond to you and try and quickly fix it. So this would be the formal process to file bugs and feature requests. So I'm going to go ahead, start this project, and I'm going to create a new IMAT project. So I have to give it a project name. I'm going to call this Mine A. I need to specify where I want it installed. So I'm using Ubuntu, and that's why it's got this path, but I'm happy with this path where I've got it stored. You have to give the mine a name, so I'll give it Mine A again, just for the sake of this training, but it's nice if you actually write the mine's full name out, because this name is used when movies are created in IMAT, and in future when we add reporting capabilities to IMAT. You need to specify in which time zone the mine operates. This is obviously the time zone that I'm in. It sets your default time zone. And again, for the sake of this training, just to keep the mine's data private, I'm just going to leave it in my time zone. But it is extremely important to get the time zone right, because everything in IMAT is time-centric. The concept of time is really important. For example, if we import seismic data, we want to have the correct date associated with that seismic data. And if we have built, for example, a numerical model, and we assign a time and a date to a mining step, and we want to compare modeling results versus seismic data around that time period, we want to have the time correct. So the concept of time is extremely important on IMAT, and that's going to flow even further in future when we start introducing modules in IMAT for creep modeling, etc. The mine's reference system is also very important. For this mine, the x-coordinate increases east, y north, and z up. Getting the reference system is correct is very important, especially because I've found that for various mines, if you import, for example, CAD data, the CAD might be stored in the east-north up coordinate system, and sometimes the seismic data lives in a northeast up coordinate. And then in the past, we used to manually go and correct this. So the idea is to get the mine's reference system or reference coordinate system correct first off, and then there's tools later on in IMAT that allows you to easily convert between the coordinates. And then the length unit, whether the mine uses meter or feet, and then finally a reference coordinate. So sometimes mines they operate in a very large local coordinate system. For example, the x-coordinate or the y-coordinate is extremely large. And then what we do in our flat 3D models is we offset all of those to be around 0, 0, 0 for flat 3D to help it with its precision and make the model solve easier. But for IMAT, it's extremely important for 3D rendering because our 3D graphics cards uses floating point precision and not double precision. It's important to offset the coordinate so that the 3D rendering of the mine is accurate and not there's a typical thing that happens called jitter. For example, if you rotate the scene in that large coordinate system, the mine plans jitter. So this will offset it. For this particular mine, I'm not going to worry about the coordinate system, although anything above 100,000 for the X and Y coordinates, I would recommend to choose a coordinate somewhere at the center of the mine, and then such that IMAT can automatically offset it for you. Once you've entered the reference coordinate once, you do not have to change that coordinate manually later on. So I've just created the IMAT project. You can see in the bottom right hand corner, that's where my project location is. I've got a license active. It also gives me my mine name at the top. On the left hand side, we've got the project explorer. This is basically a tree view of all the plugins and modules in IMAT. In the top here, we've got a properties window. This is a context-sensitive properties window. So based on items that you click on, certain properties becomes available. And then at the bottom, we've got an information window. And this information window is extensively used. Every plugin, for example, that you click on, every item should have extensive information. I'll give you a good example. For example, the local magnitude scale that the Mine uses. I'll explain in a moment what that means. This gives you information about what the local magnitude scale is. And then further, for example, if you want to create for example, import a block model, you'll see that there's how-to, and this is where the how-to videos are linked. So this is a video demonstrating how to import and visualize block models. So as these how-to videos, as I explained earlier on, becomes available, this is how you can access the how-to videos. And this is just one example. So the information window is used extensively. There's also a controls window that allows you to modify things in the 3D viewers. And then there's obviously the 3D viewer itself. It uses a modern 3D engine used for actually in computer games. For those of you that have children that knows what the Minecraft game is, this is the same engine that's used in Minecraft. So it's really fast and it's modern and it's easy to use. Yeah, and I hope that over the next few days that you'll actually see that the 3D engine is quite fast, and we can actually populate it with much content, and it won't really slow things down. And it's because it's a modern engine. And I'll go back to the Project Explorer and just explain each one of these items quickly. So all of these items that are highlighted in bold are modules or plugins to IMAT, and these items are hidden or new items appear based on a license that you've purchased for IMAT. So let's say, for example, you've only purchased the FLAC3D module in IMAT, then typically what it would look like on your side is the FLAC3D options, the charts options, bore holes and block models will be hidden, seismic data will be hidden, and spatials will be visible. So this is for a person that's only purchased the FLAC3D option. This is what their version of IMAT will look like. If you purchase only the seismic options, then your IMAT version will look different. And then in my example, I've got all the licenses for IMAT for all the modules currently. So it shows everything. That is one way that we use to make the user interface or to try and keep it simple. For software developers, it's usually quite complicated to keep the software simple. The more features we cram into the software, the more complicated it becomes. And people quickly lose interest when the software becomes complicated. And that's one way how we try to make the software or try and keep it as simple as possible. If you're a user that's not interested in every single plugin in IMAT, the software will automatically hide the modules that's not applicable to you, and in that way it keeps the software simple. You'll notice that there's one item that's not highlighted in bold. This is called the project settings item. The project settings item are settings that applies to the current IMAT project that's shared amongst all the other plugins. So for example, the seismic data, if you want to visualize it, local magnitude is an important item. So it refers to the global local magnitude scale in IMAT. FLAC3D, for example, uses the in-situ stress at the mine. So once you've set the in-situ stress once in the project, every FLAC3D project or model that you're going to run is automatically going to inherit the default in-situ stress that you've set. You can later on override that, and I'll show you how you can override that. But yeah, the idea is that you set it once, and if you create a new FLAC3D project, it will set that automatically for you. Furthermore, you'll notice that each of these plugins, these bold items, they've got a button on the left-hand side here that only shows that items. For example, I've selected the Geometries plugin and it only shows that item's data in this window. Sometimes, especially once the project's quite big, you've got, let's say, for example, 5 flat 3D projects, Seismic Data, hundreds of geometries imported. Navigating this tree might become complex and slow. So the idea is to use these items if you quickly want to, for example, select an item in the Geometries plugin. Just select the Geometries plugin here and all other items will be hidden for you. All right, I think what I'm going to do is I'm going to jump over into my presentation and just cover a few topics on the presentation about seismicity. And then we will jump back into IMAT and we will import some seismic data and apply what we've learned. So a month and a half ago in Toronto, we hosted this workshop on seismicity numerical modeling and how you can use seismic data to improve your numerical models. And I will just cover certain topics of that in this presentation, and I'll quickly go over some of them, and then we'll jump back into IMAT. So this presentation covers basic microseismic concepts. For example, what's the definition of a seismic event? What's the difference between seismicity and aseismicity? How does P&S waves work? We might actually skip this for the session. What is seismic event location, and can we actually trust seismic event location? Two very important seismic parameters, basically the core of all other seismic parameters, is seismic potency and seismic energy. Magnitude scales. I want to briefly explain the difference between local mine magnitude and Richter magnitude. At many places and mines that I visit, I see that there's confusion between what the actual mine local magnitude scale is and Richter magnitude scale is. We will probably skip radiation pattern, but radiation patterns are sort of an introduction to source mechanisms and beach balls, something that we should use very frequently, especially when we do modeling. And then for this session is how I will talk about how we can use seismic events to test the input to our numerical models. For example, the in situ stress state. And then maybe later on we can cover on how the topic on how we can actually extract seismicity from our numerical models. So first of all, what is a seismic event? A seismic event is a volume of sudden inelastic deformation. And the word sudden is extremely important. It's a brittle response. It's something that happens quickly, and it's inelastic, meaning it's permanent deformation. So it's as a modeler, it's extremely important to understand the quickness of the process and understand that deformation is permanent. This is not to be confused with an aseismic process. And the reason why it's important to understand the difference between seismic and aseismic is that when we run a flat 3D model, the majority of the plasticity or the inelastic deformation in our model is aseismic. When we apply strong damping to our models, we basically lose the concept of time. We remove energy from our system. And we do model plasticity in our model, but the majority of that plasticity is aseismic. It is not seismic. And there are some tools that we can use to try and determine whether that plasticity is seismic, but it's important to understand that the plasticity is aseismic. And what is the difference? So this illustration here at the bottom basically explains what the difference is. So if we take the San Andreas fault, for example, and an eruption starts on this on that fault, typically what happens is it starts off very slowly. We've got a small area of deformation on that fault, the nucleus. The eruption starts very, very small from that slowly from that process, from that point. Because it's so slow, it's considered to be the stable or quasi-static phase, and this time can be days, months, years. It's very, very slow, but it's still inelastic. It's still permanent deformation. It's just very slow deformation. At a certain point, that rupture starts accelerating. So it becomes faster, the crack grows faster into this unstable accelerating phase, but it's still aseismic. It's still something that a typical seismic system cannot record. That deformation, or the frequency of that deformation, is too slow. Then at some point, the rupture starts rapidly accelerating. It reaches a point where it releases a lot of energy very quickly, and only this part is considered to be seismic. That is typically the earthquake, the waves that we feel when that rupture occurs, and we hear about it on the news, and they explain it to us in terms of Richter magnitude. That is the seismic part. But the majority of the deformation initially, that took a very long time to occur, was aseismic. And in our numerical models, it's exactly the same. The majority of the plasticity in our numerical models is aseismic, not seismic. So often when we write reports or we look at reports from consultants, they try to calibrate their numerical models with seismicity, and they even use parameters such as plastic energy and compare that to the seismicity. And often they overestimate how much seismicity the model actually produces, and this is why. It's because the majority of that plasticity is aseismic. I'm going to skip seismic waves. For those of you that's interested, I'm happy to share this presentation. Here's some nice YouTube links to explain to you the difference between the various kinds of seismic waves that we get. As a seismologist, there's two waves that are important to us: the pressure wave and the shear wave. We don't really care too much about the Rayleigh waves or Love waves. And for those of you that's interested, P waves, the pressure wave, typically propagates around 5,000 to 6,500 meters per second in hard rock. And the S wave, the slower wave, between 3,000 and 4,000 meters in hard rock. And these are just examples of a seismic wave. I'm not going to go into too much detail about what this is, but as a seismologist, our goal is to try and find the P and the S wave arrivals, and we use that information to determine where the event locates, as well as estimate the source parameters at the event location. I'm also going to skip over how we locate seismic events, but I do want to make the point that when we look at seismicity, whether you're a consultant and you look at seismic events from a client, or you're at the mine and you're looking at seismicity, is do not necessarily trust the event location. There are so many assumptions that, first of all, go into locating the seismic event, and secondly, once we do have a location, for example, how close the event locates to excavations, how the ray paths that the waves traveled. So do not necessarily always just trust an event location at the XYZ coordinate that we get from our seismic system. In some areas of your mine, the location might be accurate, and in other areas it might be poor. And especially when you do calibration of your numerical models to seismicity, you need to account for inaccurate event locations. There are other seismic source parameters. I've explained the definition of a seismic event. It's a sudden inelastic deformation. Volume of inelastic deformation. So volume of inelastic deformation, basically plasticity. When you look at a seismic source parameter, the seismic potency parameter, it basically defines the volume of inelastic deformation, and its unit is in cubic meters. And I will be mentioning seismic potency many times over the following days, because I personally believe that that's the more accurate seismic source parameter that we can extract from a numerical model. For those of you that work with seismic moment, seismic potency and seismic moment is basically the same thing. It just uses this equation. Seismic moment is rigidity times seismic potency. So it's just a linear relationship between the two. So if you work with seismic moment, that's fine. Just keep in mind that it's potency scaled by rigidity. I also mentioned that a seismic event is a sudden process. Now, the suddenness of this process, the speed at which this happens, that is the seismic energy part. And that part is, well, first of all, the seismic system providers, or the people that process the seismic data, the estimate of the seismic energy is usually a lot less accurate than the seismic potency for a particular seismic event. And secondly, if we want to model seismic energy in our numerical models, we theoretically should remove all damping from the system. If we really want to properly model the seismic energy of a process of failure in our models, we need to turn off damping in our flag 3D models, and we need to allow for the pressure and the shear wave to propagate to accurately estimate, or more accurately estimate, the seismic energy. But because we apply damping, we actually want the system to be near quasi-static equilibrium all the time. We're removing a significant amount of energy in the system. So we cannot really model seismic energy. Now, I mentioned earlier on that some people use some parameters like plastic strain energy, and that's all fine. It's just it's important to know that if you properly want to model energy, you actually need to allow the waves to propagate through the medium. So using energy, in my view, is less accurate than using just seismic potency and the plain inelastic deformation in the model. Usually, I find that if you do a calibration, it's much easier to work with seismic potency than seismic energy. There are some other source parameters like frequency, corner frequency, and all of those I'm not going to mention now, just for the sake of time. But there's some of them that can actually help us as well. And before I jump back into IMAT, I want to just spend 5 minutes on seismic event magnitude, local magnitude, Richter magnitude. Often I read reports or look at reports on mines where people actually refer to mine magnitude as Richter magnitude, and it's not the same thing at all. Mine local magnitude and Richter magnitude are two completely different things, and you cannot even convert between mine's local magnitude and Richter magnitude. And I'll explain in a moment why. Magnitude uses a logarithmic scale. So in theory, a magnitude 7 event, for example, is 10 times larger than a 6 event. It's not 100% 10 times. It depends again on the magnitude scale that you use, but in theory it's roughly about 10 times larger. It's also important to note that magnitudes can be negative. We work with microseismicity in our data, so magnitudes can be negative. So micro earthquakes typically range in the order of like -5 to 3, and this is a very rough estimate, but most of the time we actually work with negative magnitudes, whereas in crustal earthquakes, magnitudes are only considered large once it's maybe 3 or 4 or bigger. So yes, it's two completely different scales that we tend to work with in mines compared to crustal seismology. And usually, if I do in-person training, I'll just give you an illustration of the size of an event. So typically, a magnitude -3 event is a crack with diameter about half a meter to a meter. And if we look at a -2 or a -1 event, we start entering maybe 4 or 5 meters, the crack or the rupture length in the rock mass. If we look at maybe a magnitude 0 or 1 event, we're talking about 10 to 100 meters crack. If we're talking about a magnitude 3 event at a mine, it's typically a rupture in the order of the length of the mine almost. So it quickly scales up. So Richter magnitude is a function, distance and the logarithm of the peak amplitude. Basically, what Richter did was he took it took a few measurements of earthquakes using a Wood-Anderson seismometer. Now, we don't typically use Wood-Anderson seismometers, first of all, in the mine. We don't have those. But what he did was for crustal earthquakes is he would look at the maximum amplitude of one of the waves that were recorded for that particular earthquake, look at the distance from the earthquake, he would plot it on this, create this plot, and then he would create this fit, and this is how Richter defined his magnitude. It is for an event, it's a function of distance and the logarithm of the maximum amplitude of the wave that was recorded. Mine magnitudes are completely different. A mine's local magnitude is a function of the log of the seismic potency of the event, plus another constant times the log of the seismic energy of the event, plus a third constant. So it's a function of seismic potency and seismic energy. Richter, as I mentioned, is a function of distance and amplitude. Mine is magnitude is a function of potency and energy. It's completely different things. And we cannot compare mine's local magnitude to Richter magnitude. There are some people that try to play tricks to do that, but it will be quite inaccurate. Furthermore, every mine uses its own values for the constants A, B, and C. For example, one mine might choose to make B 0, so completely ignore seismic energy, and have a value for A and C. That's typically the Hanks-Kanamori magnitude scale or the moment magnitude scale. Quite a few mines use the moment magnitude scale. But there are other mines, for example, in Australia, that considers the seismic energy part as well. And there are even mines that only consider energy. So A and C is 0 and B is 1, for example. The problem with this is if you're an engineer, a particular mine, and for that mine that you've got your own values for A, B, and C, you design TARPs, for example, re-entry protocols based on certain magnitude events at your mine, and then next month you move to a different mine. What I often see is people try to use what they've learned at their first mine in terms of TARPs and try to take it over to the next mine and try and use the same methodology, try and apply the same procedures. But it's not necessarily correct, because if that mine's magnitude scale is different to the first mine, then none of that assumptions hold anymore. For a consultant, it's also important. We need to report information often in terms of magnitude to the mine. But the first thing that we have to do as a consultant is to try and determine what magnitude scale it is that the mine uses. So if we do two different projects for mine A and mine B, we write a report in terms of magnitude, but we're not aware that the magnitude scales might differ, then what we are writing might not be necessarily as accurate. So yes, important to understand the concept of a mine's local magnitude. One last thing I'll mention before I jump back into IMAT is sometimes mines design TARPs and protocols in terms of magnitude. So a good example is often we see, let's say, for example, a magnitude 1 or a magnitude 2 event at a mine causing significant damage. And tomorrow we see another magnitude 1 or 2 event causing no damage at all. And the question is why? Why can one magnitude 2 event cause significant damage and the other one not cause any damage at all? And then the follow-up question is, how do we design mine protocols and procedures based on magnitude? The answer is quite simple. You can see that, as I mentioned, local magnitude is a function of seismic potency and seismic energy. We can get magnitude 2 for an event with a large potency and small energy, or the opposite, a large energy and a small potency. Both of those events can equate to magnitude 2. But the event that had the larger energy will be the one that causes the most damage. So if you have that event that There's typically that classic slip type event on a structure close to mining excavations. That's stress driven. That one typically has higher energy, and that will be more damaging. On the other hand, if you're in an event that's got more potency, more inelastic deformation, less energy, it typically means that the event occurred maybe in a lower stress region or already fractured rock. So that's why we observe less damage. But again, both events can equate to magnitude 2. So yeah, that's just another good example why local magnitude or magnitude is not necessarily a very good parameter to look at when we when we analyze seismicity. So I think I'll end it there. The first thing I'm going to do is I'm going to import some mine geometries. Then I will import some seismic data. We will import the mine's block models. And then tomorrow and Thursday, we will build some flat 3D models. So the first thing that I actually should do is ask the mine what magnitude scale they operate in before I even import seismic data and look at that information. The default magnitude scale that's applied in IMAT is known as the Hanks-Kanamori or the moment magnitude scale. And for those of you, as I mentioned earlier, that's interested in knowing how it's calculated, if you click on it, the information window will show you how it works. But Hanks or the moment magnitude scale constants are defined as default in IMAT. And you'll notice that the energy coefficient in the magnitude scale is 0. So moment magnitude scale completely ignores seismic energy. This is a very good point. So if we are going to compare model energy with seismic event magnitudes or somehow try to make a relation to it, we cannot, because if we choose the energy portion of our magnitude scale to be 0, how can we relate model energy to mine magnitude if our magnitude scale ignores energy? So it's important to, this is probably the first step that we should do when we get to create the IMAT project, is make sure that our magnitude scale is correct and it matches with what the mines provided us. All right, so let me jump in and use the geometries plugin. I've got, I'll just drag this over onto the screen. I've got data for the specific mine. I've got a block model for it, geometries, I've got seismic data, and also the seismic system. I'm going to import some geometries for the scale, and it's actually quite simple. You can manually import geometries by right-clicking on one of these folders in geometry and importing the geometries. Now, we support various geometry formats, and soon, hopefully, I will have support for BTK format as well. But these are the default formats that we do support. You can simply right-click, import the geometries, or you can, on any one, create new folders manually. For example, if I can give it a name, geometry B, and this will create additional folders here. So you can manually import it, or you can simply select the items. Now, in each one of these folders, I've got STL files. You can select them, either the STL files individually, or the folders combined. You can just drag and drop it into IMAT, and it will import that for you. So I'll just give it a second. It's shouldn't take too long. We created all those folders automatically. And let's turn on, for example, my tunnels. I've got an extraction and undercut level for this mine. If you expand it, you'll see the items under that folder. You can manually turn it on. The navigation for the 3D viewer works exactly like other Itasca software. So right-click to rotate, shift and right-click to pan, and mouse wheel to zoom. And then you'll also notice next to each one of these folders, there's an eyeball. So in this example, for the eye is closed. Here, the eye is open. When it's open, it means an item under this folder is currently visible. And you'll see many plugins all over uses this. This is to quickly hide and show all items under that specific folder or for that specific plugin. So And to turn it on, for example, all I have to do is just click on the eye and it turns back on. So I will also turn on the rings, maybe look at some drawbells, all of that. I'm not going to, maybe I'll show one instance of the code. I'm not going to show all of them, but I've got a code geometry. And yeah, so I've just quickly imported all the Mine Geometries. For the Geometries plugin, there are various tools that we can use to help us in terms of building numerical models, cleaning up the geometries. So typically, steps that you would have done in Rhino and Griddle, you can do automatically in IMAT. So one example is, let's say, I'm just going to hide the K, for example, and I want to randomly color the rings. I will select my rings. If you select them and right click, there's a toolbox option, and I'll just use the randomize colors, and that gives us a better representation. We can actually more easily see different geometries. There's also tools like the shrink wrap feature in Rhino that you can use. It basically wraps a closed surface around all the geometries. I'll show you how this works. So it is a grid-based method, and hopefully it won't take too long in this example. I'll just call this my combined excavations. Well, actually, this will actually be just rings, so it will shrink wrap all the rings combined. And okay, it shouldn't take too long. So this was using a 10 by 10 meter grid. I'll just show you what this looks like. This is what the shrink wrap version of that looks like, using a 10 by 10 meter cell size. And obviously, as we make the cell sizes smaller, the shrink wrap becomes more accurate. For those of you that's interested as well, when I presented just over a month ago about an auto-meshing intersection algorithm, this is now in IMAT. There's an intersect wireframes option in IMAT, and I will quickly just illustrate how that works with a different project, and then I'll come back to this. I believe this to be an important feature that will save all of us a lot of time, especially when we build our numerical model. So I'm just going to quickly jump into a different project and show you how the auto intersection works. So I'll close this, open another project. Just bear with me for a second. All right, so I've already got some shrink wrapped geometries here, but I'll go through the entire process. So I've got structures. I'll show you what they look like. These are structures for mine. They are not intersected, and our goal is to intersect them and clean them and make sure that they work well for inside Flat 3D. So what we do is we select all of our geometries, right-click, use the Intersect Wireframes option. There's a few options that we need to select. First of all, do we want to remodel the structure? So I'll just cancel this and show you why we want to remodel. So here's a structure, for example, that's not entirely smooth. It's got these funny sharp bits, and this might actually cause locking in our model. Also, some structures actually have holes in them that I want to automatically close. So the remodel feature basically fits, it does a new surface fitting to the structure, and it remodels the structure. Second, if you had an existing Flat 3D grid, so I've got in this particular project, I've got a Flat 3D project with an existing Flat 3D grid, an arbitrary grid with refinements already. You can cut these structures into that grid and with existing refinements, and I'll show you examples later on. I'm not going to use that because it does take a little bit of time. I'm just going to use a regular grid for this example. And then you need to specify smoothing cycles, aspect ratio for triangles, or the maximum aspect ratio for triangles. And the algorithm also does termination for you. So for example, if I want this structure to terminate on this blue structure, you can specify a threshold, and it's basically based on area. So I can say if 20% of the structure area is located on the other side of the structure that I want it to terminate on, it needs to auto terminate. So I'll just jump into this. It shouldn't take too long. So it's currently just rebuilding. It's finished rebuilding all of that. And now it's busy slicing it into the mesh. Now it's performing the termination. So it's doing the auto termination. And then finally applying some smoothing to it. It's nearly done. So it's finished, and it says it's written out all the new geometries in the geometries plugin. So I'll just turn, and the intersections plugin. So here's all those intersections. So it wrote out all the intersections for you. So I'll just zoom in, and you can see these meshes are now triangulated. And if I look at the intersections, for example, you'll see the intersection should theoretically be perfect. And for example, this structure that previously were intersected this structure over here, that's now properly terminated for you. So yeah, in most cases, this works quite well. I'll just zoom in this area as well. You can see the intersection of those structures. And the idea is there's two ways that we can use it. I showed you the manual process to using the geometry to simply do the intersection. You can now take this as STL files into Gradle and go do some further cleanup if you want, or some more meshing. What this algorithm also does is it writes out the boundaries of those intersections. So you can take this straight into Gradle and go fill them with tetrahedrons. So you've got all the structures as well as the boundaries, and you can just take it into Gradle and follow normal workflows if you want to do it manually. The other way that you can do it is how you can actually use it inside a Flat 3D project with an existing Flat 3D grid. Also, I mentioned that this algorithm can use existing Flat 3D grid to take into account the mesh degradation. So I'll show you these structures. And I will just also randomize their colors. So it's just turning on all of those quickly. And for this particular example, just bear with me, so it's just busy loading all the structures. For this particular example, the Flat 3D grid, or the octree grid, had degradation in it. So we started off with coarse cells, and we went in certain areas, we went in, we had finer cells. So just bear with me. Actually, here you can see an example. So I'll just zoom into, apologies for that. So I'll just zoom into this area. So this red structure, we started off with a octree grid with core cell size, and as it cut the octree mesh, where we had areas of fine identification, you can actually see the sizes of the triangles on the surface becoming smaller. So effectively, what we've got now is we've got a mesh that can be cut in directly into an existing Flat 3D grid that's finer. And similar to the other example is you've got the boundaries as well, and you can see here where we had the coarser zones, we've got coarser boundaries, and the boundaries actually goes quite close in those areas where we had smaller zones. In terms of geometries, I just want to see if there's some other tools that might be useful to use. So in the toolbox, there's tools to you can simply remodel it, tools to smooth the mesh if you had it. You can combine geometries into a single geometry, or you can split them. There's tools to simplify it. So if I had a structure, let's say any one of these structures, and I'll show them as lines, you can simplify that by basically reduce the number of triangles on the surface, and say I want to try and aim for at least 50% or half the amount of triangles that I've currently got. So it actually removed, it removed 84%, so it removed quite a lot. So if I look at this now, you can see the triangles are quite larger, and I still retain the original shape of the structure. So there's simplification tools if you wish to use those. You can move your geometries. So as I mentioned earlier on, if you've got a geometry that you've just imported and you want to move it to a different coordinate, you can use this to do that. You can clip it with spatials and assign dates to them. Assigning dates to geometries are quite nice, especially if you want to use the Movie Maker plugin. I mentioned that the concept of time in IMAT is quite important. So if you create a movie and a geometry's got a date assigned to it, you can actually get geometries to appear and disappear according to date for that particular geometry. When you create movies, or whether you manually step through them. So I'm not going to assign dates to these geometries now. I'm going to import some seismic data, which have already got dates assigned to them. And then I will show you how to create a movie or manually use the time stepping feature to step through the data. So let me hide my structures. I think I've spent enough time with it on the geometries plugin. Let's import some seismic data. So to import the seismic data, I'll use the Seismic Data plugin. I'll create a new seismic data set, and you can create as many data sets as you like. This one I'll call the Mine data set, and I'll maybe even name it Mine data set 1, because we can have 2 or 10 data sets from the mine. We can also have a data set that we create from a numerical model, so you can have as many data sets as you like. When we expand this, we can view the information. Obviously, in this example, I've just created a new data set, so I've got no data, and I can see that in the information window. So I need to import data. To do that, similar to every other tool in IMAT, it's a right-click functionality. You can import the data. You can import an arbitrary CSV file, or you can import the fixed IMS EVP format, or if you are an MXWrap user, you can import the MXWrap EVP format. IMAT is based on importing, or mostly based on importing CSV files. So typically, when we get data from a mine or look at a specific data, people send it to us in terms of a CSV format, but that format can be random, basically. The columns are not fixed. So IMAT's got a generic CSV importer, and I'll show you what that looks like. So you first of all select a CSV file, and then you as a user need to specify in which columns to find what information. And it will probably be a bit more clear when I import block model data later on, but you need to specify what the CSV format looks like. So first of all, is the CSV file actually comma separated or space separated? Because often the columns are separated by spaces in that file and not commas. So you need to specify whether it's comma or space separated. If there's a date and time in the file, what is the format of the file? And this typically follows the Excel format for specifying days, months, years, hours, minutes, seconds. And here's an example of what these definitions mean and how to specify them. So a typical date, if I use this format, would look like 01 January 2019, for example. That's what if the, this format would look like if you had this specific date. And then I need to say, well, I've got a column for time in column 4 or 5, for example, a column for date in column 6. And the locations of the events can maybe be found in columns 1, 2, and 3. And same for some of the other source parameters. You do not have to select every single seismic source parameter, and those will, for the seismic events, that will just be considered 0 or empty, and it will be ignored if you want to look at that and do analysis on that in IMAT. You can specify only a few, for example, and you need to specify in which columns to find that. For this particular example, I don't have a CSV file of seismicity. I've got an EVP file, so I'm going to import that. So right-click, import an EVP file. I'll browse to my seismic data, and here I've got the EVP data. Now, one step after importing it, I've specified my IMAT project to have an east-north up coordinate system, but for the particular mines data that I want to look at, the seismic data and inside the EVP file was actually defined as northeast up. That means the X and the Y coordinates in the file had to change, as well as the moment tensor information in the file. The tensor information also had to change. So you can specify, first of all, whether you want to convert the data. If you trust that the data is already in the correct coordinate system, you can simply select OK. Or if you need to convert it, you can say, well, my import data set was in a northeast up coordinate system. And you can even convert between meter and feet. For this particular mine, the data that I looked at, the IMAT project was defined in terms of meter, but the CSV file data, the information was in feet. So we even need to convert, it can convert between meter and feet as well. For this example, I do not have to convert the data is in the correct format already. So I've imported 216,000 events. Now, if I click on my seismic data set, I can see what the events, how many events there are, how many source mechanisms or moment tensors, beach balls there are, what's the time range of the data set, the typical local magnitude range and seismic potency range, and I'll probably add some more source parameters in future. The first and probably the most simple thing that we can do is visualize the seismic events simply by turning that on. So there's a rule in IMAT. If you've got more than a certain number of events, it actually doesn't render the sphere of the event. It renders them as pixels, and that's done purely for optimization, is to keep the 3D viewer rendering fast. You can change that number over here. When you click on the events in the properties window, you can change that number. If you really want to visualize 1 million spheres in the 3D viewer, you can change this value to 1 million. It will be slightly slower, but what I'll do maybe is I'm going to just quickly jump ahead and I'm going to apply maybe a local magnitude filter to show you what the spheres themselves look like. So I'm going to create an ML, call this my local magnitude filter. I'm only going to look at events above magnitude -1. If I apply that, let's just see. Oh, there's still more than 10,000. Let's make this 0. There we go. So now I'm looking at all events above magnitude 0. I can see that there are 355 of them. 341's got source mechanisms. This is a magnitude range. There's a seismic, or there's a legend. The events are currently colored according to time. I'll show you in a minute how to change that. We can copy the legend into the 3D viewer if we like. And we can move it around. When we create movies or screenshots, for example, we can individually click on each one of these events to get its information. I'll do that in a second. I'll just show some different coloring and sizing parameters first. So I mentioned that the events are currently colored according to time. You can change that to a different source parameter. For example, now I'm coloring by local magnitude, and I can easily see where the largest event is, that one. You can color it by seismic potency and some other parameters as well. You can fix your color ranges. You can choose different color maps. If you don't like the default coloring scheme in IMAT, you can, I just chose this peach coloring scheme. That's obviously not ideal. Or plasma. There's many different kinds of color legends in here. The default one is the turbo color scale, one that's used in, I think, Python or MATLAB. You can step it if you want to have a fixed number of intervals. You can reverse it if you want. The events are by default sized according to local magnitude, but you can also size them according to log potency. You can change your ranges. Say I want my minimum sphere size to be 5 meters diameters and my maximum 20, and I can change all of that. So now it's between 1 and 20. So it's quite powerful in terms of visualization. Okay. In terms of focal mechanisms, beach balls, you can visualize the events in terms of beach balls. So I didn't go into any detail on how to interpret beach balls in the presentation earlier that I showed. Beach balls are probably one of the most useful things as from seismic data that we can use to determine actually what the rock mass is telling us what's actually happening. So what I'm going to do is I'm just going to make my events a bit larger so you can see what these beach balls look like. So again, remember, I'm currently looking at events only above magnitude 0. What I'll do is maybe make it -1. So you can see this mine's got plenty of source mechanism data. The first thing that source mechanisms can do is it can give us a proxy of the in situ stress direction, so the vergence stress direction. So beach balls can be decomposed into what we call principal axes. The pressure axis is basically a proxy of the sigma-1, what sigma-1 is doing at that event location. And we can see, if I go into a plan view, I can already see what the seismic data is telling me, what sigma-1 is doing. And this actually maybe, if I just I'm just going to turn a cave on, so it will give us a better idea of what sigma-1 is doing here. And I will change my folder just for visualization, so it's easier to visualize. Let's see what it looks like if I make it -0.5. That's probably a bit better. I can see what sigma-1 is doing around my cave. So that's the pressure axis. The null axis, or the B axis, is this direction of sigma-2, the proxy of sigma-2, and then the T axis is our tension axis, the proxy of sigma-3. So sigma-3 in this location is pointing towards the cave, and above the cave we can actually see a strong rotation. And as we expect, sigma-3 points towards the void. So this is already one extremely useful feature where we can test, first of all, model stress directions versus what the stress directions are of seismic data at that particular location in our model. Secondly, we can use the t-axis for cave tracking, for example. We expect, as I'm showing here, the t-axis to point towards the cave. So we can do cave tracking, for example, source mechanism data. If we use some of these events that locate very far away from the mine, these ones, for example, that we do not expect to be significantly influenced by mining, we use these events to test the mine's vergence stress directions before we actually input it into our numerical model. So we can test the directions of sigma-1, 2, and 3 that we're going to use in our model using the seismic data. Unfortunately, the moment tensors can't tell us anything about the magnitude of those the vergence stresses, but at least it gives us an indication of the directions of those stresses. What I'm going to do is I'm going to apply another filter and target slip type events. So I'm going to add a new filter, call it my slip event. So I'm going to focus on all events that are of slip type. and I'm going to apply it. So these are considered to be all slip type events. And if I use their nodal plane, turn their nodal planes on, the nodal planes of slip type events can be used to compare to known, or even if we don't know of structures, certain structures of the mine, but we can compare the direction of these planes to structures at the mine to identify which structure might be seismically active. Now, a moment tensor specifically for slip type events can give us one of two possible planes that slipped at that event location. We don't know which one it is that slipped, and that's why we need mine geology to identify or determine which one of those structures is that slip. But purely from visualization, if I look at these events in a plan view, I can already see some of these planes aligning here. So there are, in my opinion, without even looking at the geology, there's some structure here. So what I would typically do now is look at compare the seismic data to the structural database of the mine, see if that structure actually exists. If not, then I need to go back to the to my survey department or my geologist and try and determine what's going on there before I actually even build my numerical model, because how can I expect my model to reproduce what I observe here if I don't actually add, for example, that structure in my model? And then also, if I want to take it one step further, how can I call my model calibrated if I don't allow for this mechanism to occur in my model? And yeah, from visual inspection, I mean, we can rotate just slightly, see if we can find some other structures. So moment tensor is the beach ball. So it's our representation of the moment tensor is just visually a beach ball. But what I'm showing here is these are all the same things. So these are beach balls. You can, for example, if you look at any one of these events for slip type events, that's the nodal plane for this event. You can actually see how it aligns with that beach ball. So I've shown you how to visualize the mechanisms, how to, if we've got stress fracturing, for example, how we can use the principal axes of that tensor to tell us about the directions of the principal stresses at that event location, and how we can, if we've got a numerical model, we can compare stress directions at that particular point in the model with our seismic data and see actually how accurate it is. We can look at the nodal planes of the event to try and identify which structures are seismically active. What I'd like to mention also is often I see consultants simply using event location, event as a point in space, and correlate it with a structure. So the assumption is that the event locates close to the structure, so the structure must be seismically active, and that's not necessarily correct. What you can do is take it one step further. If you've got the source mechanism information, plot the nodal planes of that particular event and actually confirm if it is that structure that's seismically active or not. And there's a tool in IMAT that can actually automatically assign events to structures for you. So there's a chart in IMAT that you can use to identify seismically active structure, and that's called the structure response plot. So what I might do quickly, I'm going to create a plane going through this. I actually don't have a structure for this group of events, but I'm going to create a plane through here, make an artificial structure using the Spatials plugin, and I'm going to use the charts or that structure response plot to actually see if that structure is seismically active. So bear with me for 5 minutes. I'm going to do a few things. I'm going to first of all use the Spatials plugin, and I'm going to create a new kind of spatial, and I'll call it a plane. There are various kinds of spatials that we can use, and spatials are used all over IMAT. It's used for filtering, it's used for building numerical models, and I will use the spatials plugin throughout the next few days. But for this particular case, I'm going to create a plane. If I rotate it, you can see I've got the plane. This is the first example where I'm going to use my controls to modify my plane. So first of all, I want to rotate my plane around the x-axis, and I've already got a semi-decent plane already there, and I might rotate it around y as well. Actually, even more, if you look at that structure in plan view, it sits in that orientation, and I'm done. I'm actually quite happy with it. So now I'm going to right click and I'm going to create a mesh, and I call it my structure. And it saves that in the Spatials plugin. Actually, what did I cancel? Great, let's try again. Oh, done. Sorry, in the Spatials folder. So it created a new folder in here for me. So there I've got a wireframe, and if I turn my wireframe into lines mode, I can see there's my wireframe I've just created. I'll just copy that and put it in my structures folder, and I'm going to see if it's true, if that orientation is active according to these event nodal planes. We already can visually see that this might be a favorable orientation for failure, but I'm going to jump ahead, and I'm going to create a new chart, call it the structure response plot. My SR plot, you can give it a name. So I'm going to use the structure response plot to turn that on, and it will use all structures that's in my structure folder. And actually, I've got too many structures. I forgot about that. I've got too many on there. I just wanted to target this one. There we go. So how this works, so let me just click on this again in the information window. This is a structure response plot. So you define for any event a certain distance from the structure. So all events are within 20 meters from the specific structure is considered. So if I go back spatially, all events that is within 20 meters of the structure, you can change this value. Obviously, if the location accuracy of your events are less accurate, you can change this value to, let's say, 30 or 40, 50 meters. And then it looks at the nodal plane angles of these events. If one of these planes angle is within 20 degrees that I've specified here, it will assign that event to the structure. So I've got two other files in my structure folder. This all structures that we're seeing here, all structures simplified. Ignore those for now. You can add as many structures as you like. That's quite nice. You'll get a quite populated bar graph. But I can see that according to these constraints that I've defined here, that this structure has experienced 120 cubic meters of seismic potency. So this plane or the structure that I've just created is, I can confirm that's seismically active, and that should be in my numerical model. So yeah, I hope that makes sense, where we can actually use source mechanism data to determine which structures we really should target in our numerical model that are seismically active. The opposite can also be true. If, for example, we want to build a model with 100 or 200 structures in, we're obviously going to create a really nice complex model, and we can really what is the correct word? We can really actually boast about the really good model that we've created. But often, many of those structures aren't seismically active. And if we've got good seismic data, as I've illustrated here, adding 100 structures in here, for example, where there's no seismicity, our model might actually show that there's some slip on that structure, but there's no seismicity that we've actually recorded. then it could be one of the typical examples where that slip is aseismic and not seismic. So I need to question whether or not I really want to add that structure in my model or not. Okay. Before I jump into the rest of the charts, let me just see if there's something that I've forgotten. Yes, so there's a data filters option. I've shown you already how to create a local magnitude and a slip type filter. It's quite simple. You just add a filter. You can filter by distance to structure. So let's do that. I'm going to filter all events within a certain distance of my wireframe or my structure that I've created. I can filter by certain event names, local magnitude, other source parameters, events that have source mechanisms. I can filter by time and I can filter by spatial volume. Actually, maybe that's something that I will do first. I'm going to create a volume and I want to target all events within a certain volume. So let me just cancel that quickly. I'm going to turn off my plane and also turn off my structures. And I'm going to create a spatial filter to try and target these events. And only filter them. So I'll create a new spatial, and there's a few different ways I can do it, but I'm going to create a box type filter. I'll show you in a minute how we can create cylinders or ellipsoids or even NURB surfaces if we want to. So I'm going to create a box. So it creates this box, and again, I will use my control option to modify my box. So I'm rolling around the z-axis, and now I'm moving it in this direction. I'm scaling it smaller. So I'm doing all of this by rolling my mouse wheel on these buttons. You can manually, if you want more precise measurements, you can actually enter it just in the properties window. For now, I will just do it this way, and let's pretend I'm happy with this box. So I'm going to create a new filter, a spatial volume, call it my box filter or area 1, because I want to investigate what's actually happening there. I've created my area 1 filter. In the properties window, I need to refer to my spatial. I can invert it, so I can actually even filter for all events, show all events outside the box, and exclude what's in there. So I can invert the filter too if I want, but not for this example. And I've just created a spatial filter to target the events in this box. Yes, in terms of other spatials that you can create, I'll show you an example of a cylinder, for example. Cylinder, you can create cylinders. That's what this looks like. And again, you can roll it, translate it, modify the cylinder. One that's actually particularly useful, if I'll turn my box off, and let's say, for example, I wanted to filter for all seismic events within this pillar, or maybe this entire region that I've got over here. So obviously, as you can see, a box won't work here because I'll overlap with a cave. Cylinder won't work, and ellipsoid won't work. So there's a special kind of filter called a polygon or a polyfilter. So I'm going to create a new poly. This is called a polygon. So let me just quickly hide my seismic events. So I've just created that poly, and all you have to do is you move this plane using the controls for the polygon onto the area that you actually want to target, so somewhere in between there, and you just simply start digitizing. So I've just created a filter. Now this box looks, or the spatial filter looks like that. And now I've got an arbitrary filter that I can use to filter my seismic data, or even filter numerical modeling results. For example, if I want to calculate the, later on I will show you, if I want to calculate the average sigma 1 in this area, or even just one pillar, and plot it over time. this is how you can create this very special filter to target only that specific area that you want to look at, the data in that volume. So this is the spatials option. Before I end with the seismic data and go into charts, I actually want to show two movies. I mentioned earlier on how we can use the t-axis of seismic data for cave tracking. So there's this movie that was actually created in IMAT. Over time, you can see the t-axis pointing towards some void. So I can typically use this for cave tracking, for over time creating cave shapes in IMAT. And there's a NURBS option. I don't have time to actually show you completely how to build a cave in IMAT, but you can use the NURBS tool in IMAT to create cave shapes and combine that with seismic data, and you can create cave shapes over time. There's also another source parameter called seismic energy index that's extremely useful. Seismic energy index is the seismologist's parameter to determine which areas of the rock mass is stressed and distressed. Now, areas of high seismic energy index we consider to be higher stress. The event occurs in an area that's highly stressed, and with low energy, it means the event occurs probably in a region of softer rock or already fractured rock, for example, closer to a cave. So I'll show you the exact same movie of t-axis, but just using seismic energy index. So blue means low and red or color means higher energy or higher stress, and how we use that potentially for cave tracking. And again, this movie was created in IMAT using the Movie Maker plugin, and I cover color events according to energy index, and then use the energy index to define a cave boundary. Energy index is an extremely useful source parameter, especially to compare with our numerical models. I've shown you how we can use seismic data to visualize certain seismic parameters. Next thing that we can do is use seismic data to, for example, contour our excavations, and then finally I'll show you how to use seismic data to look at make various plots of seismic data to understand what's happening underground. So the one thing that we can do is let's say I'll turn off my caves and my rings, and I'm going to target these excavations down here, my extraction and undercut level. Actually even combine them into a single development. So I'll call this my combined development. So now I've got one item, my combined development, and I can contour seismic parameters on these excavations. Again, I didn't go into detail in my presentation earlier about two extremely useful source parameters. They're called ground motion prediction equations. So there are two types of these equations. There's one in terms of velocity, peak ground velocity, or that's PPV, as many people know, and then there's another one known as cumulative absolute displacement. These are equations that's calibrated for every mine. And they've, like local magnitude, each mine has got its own values for these constants in this equation. But basically what this allows us, once you've got a calibrated equation, you can use any seismic event in space, and you can calculate using this equation what the peak ground velocity was at any other point in space due to that event. So I've got a few events. Let's say I'm going to target again all events in my area 1. These events that's highlighted here, you can see some of them are quite large. What was the peak ground velocity on my excavations due to this event? And many people, for example, use support design to PPV or PGV in their support design to estimate what it should be, or more modern, if you're going to into Kaiser's method, for example, deformation-based support design, the cumulative absolute displacement parameter is the one that you can use if you want to use that Kaiser's method. But what I'll do is I'm going to say right-click, toolbox, contour seismic events. I need to choose what data set to use. Give it a name. I'll call this my PGV analysis. So I'll use this max PGV. I can select actually more than one if I want. So number of events or potency displacement estimated onto my excavations. But for this example, I'm just going to use max PGV and interpolate it onto my tunnel. So now my geometry that I've imported, I can expand it. You'll see all of them you can expand, but it's empty. But now I've contoured it, and I can view contours of PGV onto my excavations. So now the excavations are contoured. If I look at my legend, these are PGVs ranging between 1 millimeters per second to 10 millimeters per second. So it's quite low. Well, I have to mention, though, that the ground motion prediction equation, these constants, the default ones in the IMAT project, was not calibrated for the mine. So it's just the default value. So I need to actually go find out or calibrate this equation. But at least now I can use this and I can contour the seismic source parameters onto my excavations. So finally, I'm going to go into the charts. I've already shown you how to create the structure response plot, but there are other kinds of plots as well. So the first thing that I want to plot that we can use is the Hudson diagram. I'll select that, call it my Hudson plot, or this is also known as the TK plot. Looks like this. So I've currently got a slip type events filter. I'll just hide all my events. So this plot gives us an indication of what kind of mechanism. If I've got moment tensor data, what kind of mechanism the data that I've currently got filtered for this data, what kind of mechanism mostly it occurs. So this line over here is known as the DC line or the double coupler line. This is typically those slip type events. There's also another line called the CLVD line, the coupled linear vector dipole. This is also a special kind of slip type event, but the DC is a classical slip type event. So we would expect an event that locates on a structure. If the structure is active, it needs to be close to this line. So again, I'm taking it one step further. I'm not, if I want to assign events to structures, I'm not simply taking the location of the event in space and assigning that attribute, those events attribute to the structure. I first use, I use this plot as like another supplement to see whether the events actually slip type to begin with. So I can see that there's a few events that's like these negative tensile crack or crack closing kind of events. So they basically, you can see that we call them crush type events, and typically you would expect these events close to voids like cave boundaries, or maybe close to pillars, close to excavations where there's a closure of the void, these negative tensile crack. A blast, for example, on the other hand, if you've got fracture opening, like hydraulic fracturing or a blast, that would be in this region over here. We actually have fractures that open. So this plot is quite useful. You can compare different data sets. You can look at contours of the data. I'm just going to remove all filters. Basically, I'm looking at all these events that's got moment tensors now, all of these ones. And you can see the majority of the events locate here. If I start looking at the larger events, you can see, oh, there's still some of them over there. If I go even bigger, let's say magnitude 0, the larger events start moving this side of the line. So we actually have some volumetric deformation crush type. If we make it magnitude 1, see the majority of all events above magnitude 1 sits in this region. So it's a mixture between slip type and having some volumetric change. Again, this is extremely very quickly going over the Hudson diagram. Another one that's extremely useful is a Stereonet Plot. The Stereonet Plot we can use for various things. First of all, I mentioned the TPB axis, the principal axis. Let me filter all events about -1. So using all seismic data blindly, I can see roughly the orientation of sigma 1 is in this direction. If I contour it, according to Schmidt density contours, I can see sigma 1 should be oriented this northeast southwest, dipping at about 0 degrees. Ideally, as I mentioned, if I want to test the Mine's Virgin stress that we're going to use in our numerical model, then I want to maybe select a spatial filter, target these events, create the same plot, and see what the direction of the principal sigma 1 is, for example. And you can do the same for sigma 2 and sigma 3. Also, I can turn on my structure orientation. Remember earlier on, I created a plane with a specific orientation, and in area 1, these events over here, I'll just turn my plane back on in Geometries, Spatials. I have this plane. I should actually go and create a filter, but I don't have time. If I turn those events on and look at their nodal planes, I can see that there's a clear, yeah, there's too many events. Let me change my filter to look at all events about 0, okay, 0.5. I can see my plane orientation. This purple line, let's maybe make it slightly wider, 4 pixels wide, and not this ugly purple color. See my plane orientation agreeing with some of the nodal planes in that area. So again, the Stereonet plot highlights that there's some events that maybe agree with that plane that I've just created there. A Stereonet plot is also, if we had numerical modeling information, you can plot stress directions on the Stereonet plot. It can be used for so many things. Another one that seismologists often use, and especially when we want to calibrate numerical models, is the Gutenberg-Richter or the size distribution plot. For this particular one, I will use, you need to use all your events. This is the typical classical Gutenberg-Richter plot, but this is typically a moment frequency, a magnitude frequency distribution or potency frequency distribution for our data set. And when I, for example, calibrate a numerical model, I would use this plot to as one of the measures to determine whether the synthetic seismicity that I extract from my model is calibrated compares well to my observed seismic data. And then finally, what I'll show is just a time plot. Again, I haven't created a flag 3 project, so I can't look at stress data over time, but the time plot, we can plot certain seismic parameters over time, especially for seismic potency, which is a very useful parameter to plot over time and compare to modeled potency or modeled plasticity in a specific region. When we calibrate our numerical model, you can import, if you've got a CSV file with custom time data, so you've got a time and some parameter, you can actually import using this button, custom data. So again, you would select your CSV file, give it a name, data 1, and specify if it's got the time, what the time format is, and what the in which column to actually find the value that you want to import, and then it will be plot on here.